Welcome. Today, we'll be exploring problem number 274, H-index. This problem is a fundamental question often encountered in coding interviews, and it focuses on determining the H-index of a researcher based on their publication citations. We will discuss different approaches to solve this problem, evaluate their complexities, and identify the most efficient solution. Let's dive in. It is determined based on the number of citations their publications receive. Specifically, if you are given an array called citations, where each element represents the citation count for a particular paper, the H-index is defined as the maximum value of H such that the researcher has at least H papers with at least H citations each. The H-index is a widely used metric to assess the productivity and impact of a researcher's work. For example, if there are 5 papers with citation counts 3, 0, 6, 1, 5, we need to calculate the largest H that satisfies this condition. The input for this problem is an array of integers with a length between 1 and 1000, and each citation count is a non-negative integer up to 1000. The output is a single integer representing the calculated H-index. Let's look at an example to understand this better. Suppose the input array is citations equals 3, 0, 6, 1, 5. In this case, the researcher has 5 papers with these citation counts. To compute the H-index, we first sort the citation counts in descending order, resulting in 6, 5, 3, 1, 0. Now, we find the largest H such that there are at least H papers with at least H citations. Here, we see that one paper has at least one citation, 2 papers have at least 2 citations, and 3 papers have at least 3 citations. However, there are not 4 papers with at least 4 citations. Thus, the H-index for this example is 3. Now, here's another example. If the input array is citations equals 1, 3, 1, the researcher has 3 papers with these citation counts. When we sort the array in descending order, we get 3, 1, 1. To find the H-index, we determine the largest H such that there are at least H papers with at least H citations. In this case, one paper has at least one citation, but 2 papers do not have at least 2 citations. As a result, the H-index is 1. Finally, consider the scenario where all papers have no citations. For example, citations equals 0, 0, 0. Here, the researcher has 3 papers, all with citation counts of 0. Sorting the array does not change anything, as it remains 0, 0, 0. To compute the H-index, we look for the largest H such that there are at least H papers with at least H citations. In this case, no paper meets the condition of having at least one citation. Therefore, the H-index is 0. It's important to consider edge cases, such as when all papers have 0 citations, when all papers have the same number of citations, or when there's only one paper. For example, a single paper with 10 citations would result in an H-index of 1 because it satisfies the condition of having at least one paper with at least one citation. To begin, let's consider the brute force approach to solve the H-index problem. The idea here is to directly calculate the H-index by iterating over all possible values of H, ranging from 0 up to the maximum citation value in the list. For each possible value of H, we count how many papers have at least H citations. If this count is greater than or equal to H, then the condition for the H-index is met. The goal is to find the largest such H that satisfies this condition. While this approach is straightforward to understand, it involves a nested iteration, one to test each value of H and another to count the qualifying papers. This results in a time complexity of O(n squared), which becomes computationally expensive for large datasets. Additionally, it doesn't require any extra space, as no additional data structures are used. However, a high time complexity is a significant drawback, which makes this method impractical for larger inputs. Now, a more efficient approach involves sorting the citations array. By sorting the array in descending order, we can simplify the process of finding the H-index. The key insight here is that the H-index can be determined by finding the largest index I where the citation count at that index is greater than or equal to I plus 1. This eliminates the need to test every possible value of H. The process starts by sorting the citations and then iterating through this sorted array to check the condition at each step. The result, I plus 1, gives the H-index. The sorting step introduces a time complexity of O(n log n), which makes this approach faster than brute force for larger inputs. It also avoids using extra space if sorting is done in place. However, sorting itself can be avoided altogether, leading us to consider an even more optimized approach. The counting sort approach offers an optimized way to solve the problem with linear time complexity. The key observation here is that if there are n papers, the h-index cannot exceed n. Using this, we can create a bucket array of size n+1 to count the number of papers that fall into specific citation ranges. For example, citations greater than n are grouped into the last bucket. After populating the buckets by iterating through the citation list, we traverse the bucket array from the highest bucket downward, maintaining a cumulative count of papers. The first point where this cumulative count is greater than or equal to the bucket index gives us the h-index. This approach is very efficient, with a time complexity of O(n), since we only iterate over the data twice, once for populating the buckets and once for calculating the h-index. Although it does require additional space for the bucket array, the trade-off is worthwhile for its speed, especially when dealing with large datasets. Given the trade-offs, the counting sort approach emerges as the ideal strategy. Its linear time complexity ensures that it scales well with larger inputs, making it significantly faster than both the brute force and sorting-based methods. By directly grouping and counting citations using a bucket array, it avoids the overhead of sorting while still allowing for an efficient computation of the h-index. While the sorting-based approach is simpler and avoids the extra space requirement, its O(n log n) complexity makes it less optimal for extremely large datasets. On the other hand, the brute force approach, though useful for understanding the problem, is far too computationally expensive for practical use. By choosing the counting sort approach, we strike the best balance between performance and resource usage, ensuring that our solution is both fast and scalable for a wide range of input sizes. To solve the h-index problem, we need to determine the maximum value of h such that a researcher has at least h papers with h or more citations. We'll start with a brute force approach, which involves systematically checking all possible values of h. First, we take the input array citations, where each element represents the number of citations for a specific paper. We initialize a variable max_h to 0, which will store the highest valid h-index found. Next, we iterate through all possible values of h, starting from 0 up to the maximum citation count in the array. This ensures we consider every potential h-index value that could be valid based on the data provided. For each value of h, we count how many papers have citations that are greater than or equal to h. This is done by iterating through the citations array and using a counter variable to track these papers. Once we have the count for a specific h, we check if the condition count equals h is satisfied. If it is, we update max_h to the current value of h. This step ensures that we are always recording the highest valid h-index found so far. Finally, after we have finished evaluating all possible values of h, the value stored in max_h is returned as the h-index, which represents the result of our computation. The brute force approach works by systematically exploring all possible values of h, which is necessary since the h-index is defined as the maximum h where at least h papers have h or more citations. Counting the papers for each value of h allows us to verify whether the h-index condition is satisfied. While simple, this algorithm has a time complexity of O, max_citation *n, where max_citation is the highest citation count and n is the number of papers. This is because we have an outer loop iterating over possible h values and an inner loop iterating through the citations array. Edge cases such as an empty array, all papers having 0 citations, or all papers having identical citation counts are also handled by this approach. For instance, if the citations array is empty, the h-index is naturally 0 since no papers exist. The algorithm primarily uses the input citations array, which contains the citation counts for each paper. During computation, a counter variable count is used to determine how many papers meet the condition for each value of h. Additionally, the variable max_h is used to store the highest h-index found during the process. However, due to the O, max_citation *n, complexity, this brute force method may be inefficient for large inputs. Optimizations such as sorting the array or using a bucket sort can be applied to reduce the complexity. For example, sorting the array allows us to determine the h-index in O(n log n) time by leveraging the sorted order of citations. While these optimizations are valuable, the current focus remains on understanding the brute force method step by step. Let's walk through an example to see how the algorithm works in practice. Suppose the input array is citations equals 3, 0, 6, 1, 5. First, we initialize max_h to 0. The maximum citation value in the array is 6, so we iterate over h values from 0 to 6. For h equals 0, we count all papers with citations greater than or equal to 0, which includes all 5 papers. Since the count of 5 is greater than or equal to h, we update max_h to 0. Next, for h equals 1, we count papers with citations greater than or equal to 1, which includes 4 papers. Again, the count of 4 meets the condition, so we update max_h to 1. Continuing with the next iterations, for h equals 2, we find that 3 papers have citations greater than or equal to 2, so we update max_h to 2. For h equals 3, the count remains 3, which satisfies the condition, leading us to update max_h to 3. However, for h equals 4, only 2 papers meet the condition, which is less than h, so we do not update max_h. Similarly, for h equals 5 and h equals 6, the counts are 1 in each case, which is less than the respective h values, so max_h remains unchanged. This step-by-step process ensures that we evaluate all potential h-index values and only retain the highest valid one. After completing all iterations, the value of max_h is 3, which is the final h-index. This means the researcher has at least 3 papers with 3 or more citations. The h-index provides a measure of the researcher's impact based on their most cited papers and is particularly useful for assessing academic performance. While the brute force approach is simple and easy to understand, its inefficiency for large datasets highlights the importance of exploring optimized solutions. Nonetheless, this method demonstrates the foundational logic behind computing the h-index. This solution calculates the h-index of a researcher based on their citation counts using a straightforward approach. First, the citations list is sorted in descending order so the most cited papers come first. Then, the function iterates through the sorted list, checking for the point where the citation count is less than the index, 1 based. This is where the h-index condition is no longer satisfied, and the index is returned. If all papers fulfill the condition, the total number of papers is returned as the h-index. This approach is efficient with a time complexity of O(n log n) due to the sorting step, making it suitable for practical use cases. This is the Java implementation of the h-index problem, mirroring the logic from the provided Python code. The implementation sorts the array in descending order using Java's utility methods and iterates through it to find the h-index. Key differences include the use of Java collections for sorting and explicit type declarations. The logic remains equivalent to ensure the same functionality. Here, we're looking at the first example where the input citations array is 3, 0, 6, 1, 5. The first step is to sort these values in descending order, which gives us 6, 5, 3, 1, 0. Sorting the array makes it easier to compare each paper's citation count against its rank, which is the index plus 1. Now, we iterate through this sorted list. In the first iteration, the citation count for the first paper is 6, and its rank is 1. Since 6 is greater than or equal to 1, we move to the next paper. In the second iteration, the citation count is 5, and the rank is 2. Again, 5 is greater than or equal to 2, so we continue. For the third iteration, the citation count is 3, and the rank is 3, which also satisfies the condition. However, in the fourth iteration, the citation count is 1, and the rank becomes 4. Since 1 is now less than 4, we stop and return the h-index as 3, because there are 3 papers with at least 3 citations each. This aligns with the definition of the h-index, where the count represents the maximum number of papers with citation counts greater than or equal to their rank. In the second example, the input citations array is 4, 4, 4, 4. First, we sort the array in descending order, which doesn't change the order since all values are equal, resulting in 4, 4, 4, 4. Now we iterate through the sorted list. For the first paper, the citation count is 4, and the rank is 1. Since 4 is greater than or equal to 1, we move to the next paper. In the second iteration, the citation count is again 4, and the rank is 2, so the condition still holds. For the third paper, the citation count is 4, and the rank is 3, which satisfies the condition. Finally, in the fourth iteration, the citation count is 4, and the rank is 4, which is also valid. Since all papers meet the condition, we return the H-index as 4. This result reflects that all 4 papers have at least 4 citations each, and no paper violates the H-index criteria. For the third example, the input citations array is 0, 1, 0, 0. After sorting the array in descending order, we get 1, 0, 0, 0. Starting the iteration, the first paper has a citation count of 1, and its rank is also 1. Since 1 is greater than or equal to 1, we proceed. However, in the second iteration, the citation count drops to 0, while the rank becomes 2. Since 0 is less than 2, we stop and return the H-index as 1. This result indicates that only one paper has at least one citation. To summarize, sorting the citations simplifies the comparison process, and the algorithm stops as soon as a paper's citation count falls below its rank, ensuring efficiency. The final H-index is determined by the number of papers that meet the condition, and edge cases such as all 0 citations or equal citations are handled appropriately, as demonstrated in the examples. To analyze the time complexity of the algorithm that calculates the H-index, let's break it down into distinct steps. First, the code sorts the list of citations in descending order using Python's built-in sort method with the reverse equals true parameter. Sorting a list of size n involves a time complexity of O, n asterisk log, n, because of the underlying sorting algorithm. Once the list is sorted, the algorithm iterates through it to determine the H-index. This loop runs at most n times, where each iteration involves a simple comparison, which is a constant time operation or O1. Therefore, the iteration step as a whole has a time complexity of O, n. When we combine the sorting step, O, n asterisk log, n, with the iteration step, O, n, the overall time complexity is determined by the dominant term, which is O, n asterisk log, n. The space complexity of the algorithm is determined by how memory is used during execution. The sorting operation is performed in place, which means Python's sort method does not allocate additional memory proportional to the input size. This results in a space complexity of O1 for sorting. Beyond that, the algorithm does not create any additional data structures like lists or dictionaries. It only uses a few primitive variables, such as the loop index I, which also require constant space, O1. Combining these factors, the overall space complexity of the algorithm is O1, as it operates directly on the input list without consuming extra memory. Now let's look at the best, average, and worst-case scenarios for this algorithm. In the best case, the loop exits after the first comparison, for example, if citations 0, 1. However, even in this case, the sorting step dominates the time complexity, keeping the best-case complexity at O, n asterisk log, n. In the average case, for a random input, the sorting still dominates, while the loop performs up to n iterations, resulting in a time complexity of O, n asterisk log, n, overall. The worst-case scenario occurs when every element in the list is checked during the loop, meaning the entire list is traversed. Despite this, the sorting step remains the most computationally expensive operation, maintaining the worst-case time complexity at O, n asterisk log, n. Let's compare this optimized approach to a naive solution. A naive method might involve iterating through all possible values of h from 0 to n and counting how many papers meet the condition of having at least h citations. This would involve a nested loop, leading to a time complexity of O, n squared. The optimized solution, however, avoids this inefficiency by sorting the citations first and leveraging the properties of the sorted list to eliminate unnecessary nested iterations. This reduces the time complexity to O, n asterisk log, n. Mathematically, the sorting step dominates the overall time complexity, while the linear iteration step does not affect the asymptotic growth. Additionally, the in-place sorting ensures a space complexity of O1, as no extra memory is allocated. In summary, the optimized algorithm strikes an excellent balance, improving efficiency significantly compared to naive approaches. One of the most common mistakes when solving the H-index problem is misunderstanding its definition. The H-index is not the maximum citation count for a paper, but rather the maximum value of H such that there are at least H papers with H or more citations. Misinterpreting this can lead to completely incorrect calculations, so it's critical to focus on the relationship between the number of papers and the citation threshold. Another frequent issue is sorting the citations array incorrectly. Many solutions require the array to be sorted in descending order, and failing to do so disrupts the whole logic of the approach. Lastly, off-by-one errors are a subtle but common problem. These happen when you miscount the number of papers with at least H citations or make mistakes with array indices, especially when dealing with edge cases like no citations or uniform citation counts. These small errors can result in significant inaccuracies, so attention to detail is crucial. Neglecting edge cases is another frequent pitfall. For example, not accounting for an empty citations array, all papers having 0 citations, or cases where every paper has an unusually high citation count can lead to runtime errors or incorrect results. Efficient handling of these scenarios is critical for a robust solution. Another common mistake is relying on brute force methods when more optimized solutions are available, such as counting sort. While brute force approaches might be intuitive, they often fail to meet time constraints in competitive coding settings. Optimized solutions, on the other hand, can significantly improve performance and are much better suited for scenarios with large datasets. Avoiding these inefficiencies is vital to solving the problem effectively. In interviews, solving the H-index problem often tests your ability to balance efficiency with correctness. Sorting-based and counting solutions are frequent topics, so you should be prepared to discuss the trade-offs between these approaches. For instance, sorting has a time complexity of O(n) log n, while a counting sort approach can achieve O(n). Interviewers also expect you to handle edge cases, such as all papers having 0 citations or a single paper with an exceptionally high citation count. These are common traps meant to assess your thoroughness. Additionally, be ready to clearly explain the time complexity of your solution and why it's optimal. When walking through examples, take the time to explain how tools like counting arrays work, demonstrating how they map citation counts to paper counts. Finally, keep in mind that the H-index is related to other problems on platforms like LeetCode, such as H-index 2, which involves binary search, or problems like top K frequent words and top K frequent elements, which test similar skills involving counting and sorting. Understanding these connections can help you quickly adapt to variations of the problem. There are several approaches to solving the H-index problem, each with its own trade-offs. The brute force method involves iterating over all possible values of H and counting the number of papers with at least H citations. While this method is straightforward, its O(n)² time complexity makes it impractical for large inputs. A more efficient option is the sorting-based approach, where you sort the citations in descending order and find the maximum H such that the HTH paper has at least H citations. This method reduces the time complexity to O(n) log n, but the sorting step can still be a limitation for extremely large datasets. An even faster approach is counting sort, which uses a counting array to store the frequency of each citation count. This method achieves O(n) time complexity and is well suited for competitive coding. However, it may require additional space and is slightly more complex to implement. Each approach has its pros and cons, and selecting the right one depends on the constraints of the problem. For cases where the citations array is already sorted, you can use a binary search approach to find the H-index. This method works by narrowing down the possible values of H using the properties of a sorted array, achieving a very efficient O log n time complexity. However, this approach is only applicable when the input data is pre-sorted, such as in the case of LeetCode 275, H-index 2. While it's highly efficient, it's important to recognize that its application is limited compared to other methods. Understanding when and how to use binary search can help you quickly solve variations of the H-index problem that involve sorted inputs, making it a valuable technique to master for specific scenarios. Great job! We've covered the H-index problem, its approaches, and key takeaways. Remember to practice problems like this to strengthen your algorithmic thinking and problem-solving skills. If you enjoyed this session, don't forget to like and subscribe. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!